Hello everyone, welcome to Samvaad Talks. I'm Shalini Singh, a student volunteer with IIIT Branding Committee. Today I'll be introducing the speaker and the talk. So today's speaker is Dr. Madhav Rao. Dr. Madhav Rao is a faculty member of IIIT Bangalore. He obtained his doctoral degree in Electrical and Computer Engineering, Department of University of Alabama. He is actively involved in applying robotic solutions to healthcare problems, especially in the area of assistive, rehabilitative, and neurosurgical problems. He, along with his students, are actively involved in finding approximate VLSI design based edge inference solutions to few of the medical care applications. He has actively collaborated with Nimhan's faculty and has devised prototype solutions to various neurosurgical rehabilitative problems in last 4 years. He is a recipient of SERB Early Career Research Award and Vishweshwara Young Faculty Fellowship Award. He is also involved in 3 projects sponsored by Ministry of Electronics and Information Technology India, Ministry of Social Justice and Disability Empowerment India, and IBM Shared University Grant. He is a senior IEEE member and an active EMB Society member. Today he will be talking to us about robotics and edge system for transforming surgical and assistive medical care. Few robotic solutions applied towards upper limb anthropomimetic and biomimetic prosthetic exoskeleton device, lower limb DVT prophylaxis device, image-guided skull targeting system, and flexible operating system microscope to study human cadaver brain will be presented. In addition, the ongoing research on approximate VLSI design to accelerate edge computing towards automated dosage injector for epileptic patients and food detection and passenger safety will be introduced. So, I would like to request Dr. Madhav Rao to start the talk. Thank you.
Thank you, Shalini. Thank you for reading out the long introduction. So the title is Robotics and Edge Systems for Transforming Surgical and Assistive Medical Care. And then the reason for this title is I think I've been working in this area for almost more than 4 years. And so robotics turns out to be a good solution for automating several of the surgical and assistive medical applications. Edge systems, because coming from the VLSI background, it turns out to be a natural cause and move towards the edge solutions. Um, and then, of course, the reason is always making it an accelerated decision making, which is quite possible only if we design our hardware optimally. And that's why I think the title. So the first major part of the talk will go towards the robotic solutions and then the sensory systems. And I think the last 4 to 5 slides, I'll just have, I'll probably get deviated a little bit away from the surgical and assistive medical care, but I try to, bring it up that it is very, very essential in the future. Okay. So all the work has been done by the students. So I am just, I'm just a speaker, or rather I would say that I'm just assembling all their work together in one particular deck of the slides. And so this particular work has been done by IMTech students, MTech students, MS students, and they have been working very closely in the surgical and assistive robotics lab. In fact, even the SARL logo is also designed by the students. I don't have any hand in that. The SARL lab is funded primarily by the MINRO and the EHRC, and of course by the funding agencies like MIT, MSJ, IBM SUR, Digital India, and others. Okay, so moving forward. Okay, so this is the big picture of the healthcare system where we have the patients coming from the home and reaching out to the hospitals, standing in a queue, and then reaching out to a reception here, and based on their problems, they are kind of moved to the particular physician, where the physician sees the problem, and then based on the initial results, they are being taken to the particular MRI or the CT scan rooms, where the results are gathered, and then based on the results, once again it goes to a group of the surgeons, and then surgeons then plan out. A group of the surgeons comes here and then do the surgery. Once the surgery is done, post the surgery, then they go back. And within the hospital, there is a little bit of theoretical exercises being done, and then they are discharged. Right, this whole cycle of the patient going through the surgery process and then getting back to the their own home, it's kind of very, very tedious in terms of the hospital itself. The hospital currently, with the India, the growing patient population, the number of the patients the ratio of the patients and with respect to the doctors or the surgeons is kind of very, very skewed. And so if I have a very huge patient population here, and very, in this particular surgery room, we have a lot of surgeons, neurosurgeons, cardiac surgeon, for a single patient, devoting time, then I think because of the sequential, of the patient getting into the surgical room or the theatrical room, it becomes impossible to have the surgery done at a higher speed. So that is one thing which I think the current healthcare system doesn't take into account. And to assist, to have some kind of a support mechanism, can we have a robotic solutions which will help the surgeon? So instead of having a group of surgeons, maybe we can have two of them or one of them, and then the other things could be handled by the robotics, right? So that is quite a possibility. Although there are robotic surgery is not new. In fact, it is not new to the India also, but we have around 80 surgical or the robotic surgery surgical instruments available in India. But the cost is so huge that it doesn't become viable for the patients to come inside and then get that particular state of the art robotic surgery done. And hence, I think those kind of robotic surgery doesn't is not feasible, and it's not considered as a feasible solution within India. So what is the right way? The right approach is to have an indigenous robotic surgical instruments available within India, made in India, of course, and then have it run around in the operation theaters. Uh, Post the discharge, the patient goes back to the home, and then once again he has to take a kind of a new appointment or a particular date, and then along with the caretaker, he comes in, and once again he takes an appointment for the physiotherapical exercises. But again, that is kind of assisted by the staff or the nurse here in the hospital or the physiotherapeutical center. And once that is done, I think he goes back to the home. And then once again, this is periodical. It's a periodic event, so he has to come back, and then once again has to go through all this process and then go back. Now, the alternate way is, why to bring the patients back to this particular center? Why not have this kind of devices, maybe made in a portable way or a wearable way, and then deliver it or issue it to the patient so the patients can actually get it done. All the exercises, all the needed physiotherapeutical exercises can be done domestically, right? So, and this also helps in accommodating more number of patients. So looking at the hospital management and as well as the patient management, I think the robotics and then the coming up the edge solutions becomes a natural and feasible method, right? So that the load of the patient becomes less on the hospital. So for today's talk, I'll just have very crude definitions. What do you mean by robotics, edge, and somewhere there is an IoT here. Robotics, according to me, it is nothing but a actuation mechanism. It's a purely an actuation mechanism. It could be electromechanical, it could be hydraulics-based actuation. It could have sensory systems or could not. But generally, we will want to have a robotics which is slightly smarter, and that's why we have a sensory systems, and then that will help in actuating. Edge solutions, we have a sensors, and if it is possible to have a decision-making ability within this particular module, and these days we need accelerated decision-making. So if that could be accommodated, so the sensing facility as well as the the accelerated decision-making, that becomes the edge device. IoTs, as when we consider about edge and robotics, it makes it has to be defined. IoT has to be defined. So IoT, according to me, it is a sensory system as well as a communication system. So I have some kind of a physiological signal going in, and then it should be communicated probably to the cloud or to the web server, whatever it is, right? Whereas the edge system, it is more, you get the physiological signals and then get the decision making. The decision is done. Very, very useful for diagnosis or prognosis based solutions. Okay, so let me get started. So there's a range of projects I have put in this particular slide deck, and it might get a little bit exhaustive, but I think it is very important to appreciate all the students' effort, and that's why I have put all the work here. So the first one is when I'm talking about the rehabilitation, especially when we look at the hospital and then the physiotherapeutical center. The very first exercise is the upper limb exercises, and especially for the post-stroke patients. So what they generally do is a nurse will come and then they will have the patient's the fingers and then the wrist and then the elbows to be actuated, now physically. Now the question is, why not get some kind of an assisted or a programmable and a variable and a portable system done. So that's what I think student Vinay has been working on this for almost 4 years now. So he has developed a variable system, and here, this particular figure showcases that individual joints could be moved of the fingers, of the thumbs, and so we have shown some kind of a thread or a line connecting from one finger to the other side of the hand. So point number two, where the thread is moving from one side to the other side, and then so on. All right, so we have developed this particular variable and a portable solution wherein each of these individual joints are driven by the pulley system. And then on this particular palm region, there is no electronics. So this is only the thread here. And it all goes here into this particular DC motor, which is driving the thread mechanism. Right, so basically a pulley mechanism. And then this particular DC motor is again controlled by the microcontroller sitting somewhere on the back of the person who is using or wearing this particular system. So that's about the fingers and then the wrist and all. So it becomes, and all this particular portion is 3D printed, and then it is put on a plaster of Paris framework. It's kind of nicely designed, and it fits into the user arm. On this side, we have the elbow actuation. So I'll show you a video later on. And then this is a 3D printed mesh here, which fixes onto the forearm and then on the other arm. And that's how the elbow is kind of moving. So this is how the person is actually wearing the system with the forearm and then the other arm. Again, all these things are indigenously produced, so within the IIIT. So I'll say that this is kind of a variable, portable, and aimed for the domestic trials and usages. Okay. So this is kind of an actuation device. So here I'll showcase a quick video. So we have a video of this is an elbow actuation. So the hand of the user, it is at rest, so it is not putting any pressure, and the system is actually taking the elbow actuation. So there's another where the fingers and then the wrist will be moving. So person wears it, tucks it, and then based on the actuation, the fingers, there's kind of an extension movement driven purely by the pulley system. And so this could be kind of a programmable, and this could be a protocol which could be recommended by the physiotherapical doctor who is investigating the patient, and then this particular recommendation can be taken home, and then it could be used by the patient in the front of the caretaker. Right, so that's how the mechanism is developed. So in the previous set of the slides, we had seen only the actuation mechanism. So now to make it a little bit more smarter, so I think when I tried developing a sensory system, so wherein we wanted to know whether whether we can actually use it for a purely as a diagnostic measurement, whether the fingers is whether it is moving and which fingers are moving, and based on that we should be able to tell what kind of deformation the muscles has. So now there's always an electromuscular activity signals, also called as electromyography signals, so that could be picked up at the surface of the skin, especially in the forearm region. And that has been devised here. So we have a differential pair of electrodes sitting on the forearms, where we can identify the muscle fibers that is going on. But the problem here is we don't really know which finger has made the movement of which muscle fibers, or the group of the muscle fibers, whether the index finger has moved the muscle fibers 1 and 2 together, or 1, 2, and 3, and so on. So there needs to be some kind of a classification that needs to go in. So we have this, Vinay has developed this 8-channel SEMG, surface EMG sensory system. This is the PCB view of it. So the PCB board, and then these are the differential electrode clips. So which goes and then sits on or gets clipped into this particular forearm region, right? So, and it picks up the signal. Once the signal is picked up, then we don't know which signal is for what. So then so he has developed an SVM classifier so as to classify which of the movements have been performed, whether the finger 1 or the index finger has moved with respect to the little finger, or with respect to the ring finger, or with respect to the thumb. So there's a whole set of classification that has been running after acquiring this physiological EMG signals. Right. So again, this is done in a way that this is portable and a system to monitor the improvement in the rehabilitation. So the rehabilitation, every time you keep on moving the fingers, right, it naturally tends to rehabilitate, and at some point of time you will start picking up the muscle signals. Right. So that is where we can, on a daily basis we can monitor, and then finally we can say that okay, this particular the rehabilitation has worked. So this is a very small example just to visually demonstrate, the moving of the fingers and how this particular prosthetic robot is actually moving. Purely as a, it can also be utilized as a very tele-robotic rehab device, wherein the person remotely can move his fingers, and then this particular prosthetic hand can be set up in the hospital center, and then if it keeps moving, and the doctors can easily visualize it. If there is any problem here, then he knows that which of these fingers has any problem. So I'm just going to run this particular video wherein the student has moved the fingers, and the robot is moving the same finger. Right, again, this prosthetic robot, I think we borrowed it from the robotics club. Prashant, Sailesh, and Anurag had developed this for some different application, but then finally we tried to integrate this with our EMG system. Going forward, I think we are yet to complete this, but I think it's, this slide showcases that kind of an importance of this work. If we can make this on a flexible substrate, polycarbide substrate, and have our electronics. So this is the 4th channel, which Vinay had developed. And so I think this is the 2-channel system, I think possibly. And then on one side, it gets connected to the skin. And this is the electronics coming on the other side. So the chips are here, and on the other side, which is in contact with the skin, there are the electrodes. So this could be you can easily patch it onto the skin, and it could be very easily integratable to the actuation system which we have developed. So on the first layer, we have an actuation system, and then beneath that, we could have the flexible system here. And I think we were not able to do progress further on this because of the lockdown, but I think we just measured using this flexible system whether we are getting any kind of the signals after the movement of the wrist. So that's what it is shown here. Right, so once we had this surface EMG sensory system, so I had a student from Samsung, Sharmila Mani. So she did the MTech thesis, and her thesis was on this particular topic of whether we can learn the keyboard learning can be done and can be visualized or can be supervised using the Surface EMG sensory system. So generally, the tutoring is a very personalized way of it works in a very personalized way. The tutor sits right beside the musical learners, and then if he or she plays the music, then it needs to be tutored or monitored very, very closely. But this is because of the online tutoring, we have various online tutoring, but then for the online tutoring there needs to be a very special ear for the learners. And if it is not, then I think it gets really demotivated. Now so we thought about another way of whether we can actually determine the pressing of the fingers, all right, the pressing of the fingers, the temporal flow of the fingers movement using the SEMG signal, as well as the time, the duration in which the keyboard is kind of pressed. So all those aspects we can actually acquire and then see whether the learner is actually learning at a good flow or there needs to be some improvement. Right. So especially this works only for, I think, the finger-based musical instruments, and that's why we have taken the keyboard aspect here. And this shows an octave in a keyboard, and based on the pressing of the individual fingers, which is mapped to the individual keys here, we can then try to find it out. We also benchmarked this with the commercial myoband instrument. So myoband is a very commercial instrument. It's kind of very useful to benchmark that, and turns out that our only the 2-channel SEMG signal is quite capable when I consider the 8-channel myoband signal. But the myoband signal, again, it doesn't give us the flexibility to place the electrodes where we want. So in terms of the restriction, the spatially it is kind of very restrictive. Right. So I think the classifier here, I think Sharmila had used was around, it gives a, so classifier in the sense, if I move the fingers, the individual fingers onto the particular key press notes or the key notes, we can actually classify which finger has pressed which key notes here, or it classifies whether it's a chord. Chord represents, the group of the fingers pressing the keyboard. So using the LDA and then the random forest method, I think she was able to get around 80%, which is in close, approximation or in the close agreement with that of our own or the myoband results, right? Using the 2-channel as well as the 3-channel system. So I think so up till now we had seen the wearable device, so a person wearing the device. Now I think Vishal came up with this idea of developing a prosthetic hand, and not really whether it fits into a human or not. That is not the real application. We want it to be useful for as an assistance to in the surgical theater rooms. So the plan here is designing a pipeline architecture wherein this particular Kinect sensor captures the human motions, and especially the left arm. So the only one arm is kind of is captured by the Kinect sensor, and then this particular, whatever is the skeletal tracking of the left arm, is kind of mapped to the Blender game model here. So the Blender game model has, there is a model which Vishal has developed in the Blender game, and then the Blender game then tries to direct right to this particular robotic arm. And this particular robotic arm, we have tried to make it very, very similar to that of the human arm with the 8 degree of freedom. Actually, from the shoulder to the wrist, it is the 7 degree of freedom, which remains the same. The last one, fingers, I think we have tried it to make it, instead of having 5 fingers, I think Vishal has come up with a gripper mechanism. Right? So if we were to replicate the 5 fingers, there would have been a little bit more nuisances which needs to be accommodated. So it becomes an 8 degree of freedom, which is by far the lot of degree of freedom, and that's why we call it as a biomimetic, because it mimics all the aspects of the arm of the human anatomy. Right. So there are 2 ways here. One is the human mimetic actions could be replicated through this particular pipeline architecture, and then the biomimetic arm could then replicate or reproduce the actions that is being performed by the user here. Right. The other one is because of this Blender game engine module.
Topics वगैरह कुछ
because of this Blender game engine module, the user can actually teleoperate it. So the user can actually move from here, and then that could be replicated or reproduced in this particular robotic arm. Right. So that was Vishal's thesis work, and I will just show a video of this. So there are 4 modes. One is the kinematic forward kinematics, wherein it moves the individual the joints or the individual arms. So remember that the 8 degree of the freedom comes with 8 motors. So 8 powerful servo motors have been assigned. And there's a little bit of oscillation here. I hope that in the future, if you are able to fine tune the PIDs, I think it should be doing well. And this is the inverse kinematics wherein he moves the end effector. So this is the teleoperation mode, Blender game engine module. You can directly move this and then the physical arm moves in a real time, right? So okay, and there is a path following. So there is a path which has been defined here. And as the Blender game engine module moves here, it is driving the robotic arm, right? So I think we get this at the distal end. There's a little bit more oscillations here. Teleoperation. So using the Blender game engine again, the Blender game module. So we try to pick up the cup and then rotate it or whatever, or reorient it and then drop it. So that is quite possible. And applying a pre-recorded, so a movement is made and then that is kind of captured here in the human skeletal form, and then that is applied to the Blender game engine module, and that moves the physical robot, picks up the water bottle and then drops. Right, so this is kind of very useful in terms of for holding a laparoscopic probe where the other surgeon is actually doing the surgery. Although if the oscillations could be reduced, that will be very good. So in that sense, I think we are trying to use it as a assistive surgeon for the neurosurgery or the laparoscopic surgery. So the other one is on the DVT problem. So the DVT problem is kind of known as a common problem for the geriatric patients, the old patients, or for the patients who are undergoing a long time surgery, wherein the blood flow in this deep vein uh, tends to be static. So there is a blood stasis that has been formed, and then there is a rather resistance in the flow of the blood from this particular region, the deep venous, to the heart. Right. So the way it works in the calf muscles, this is basically the lower limb, and then the calf muscles where the muscles actually contract and then expand. So contract and then they relax. So when they're doing the contraction, it actually pushes the blood flow from the deep veins, and then this particular blood flow goes to the heart. And when it relaxes, there's a rush of the blood from the sole of the leg. So this is also called as kind of a soleal pump, also referred as the second heart of the human body. So if there is some kind of a decrease in the blood flow because there is no activity, especially for the post-stroke patients or the lower limb surgery patients who are recently undergone some surgeries, there's some kind of a difficulty in moving the legs. So what is the recommended advice is you move the ankle so that the blood flow can actually go through this particular deep venous system. Right. So what we came up with is an ankle actuation system. Again, this was developed by Vinay completely. And what we did was just to have the human anatomy. So what happens is in this particular, when the muscles contract, there is a flow from the superficial vein going to the deep venous system. Right. So we try to have this alternating compression and relaxation by using a blood pressure cuff on the calf muscles. So this and then this particular ankle actuation in alignment with respect to the respiratory behavior should help in moving of the blood flow to the blood. So what we really wanted to do is have this particular system and then do the actuation and then see whether we can get the blood flow improvement. So whether there is an enhancement in the blood flow. And then I think somewhere during the discussion, I think with Professor Vinod, so Vinod suggested why not we get the ultrasonography device testing done. And that's why we used the ultrasonography Doppler device. Dr. Arvind from NIMANS helped us in getting the Doppler results. And so although I don't understand this particular portion, I think what Vinay says is this is where there is a huge spike in the blood flow. so around 20 centimeter per second or something. And so that results kind of what validates that this indeed the ankle actuation and then the compression, the alternating compression and relaxation of the calf muscles helps us in enhancing the blood flow. So this device was also acts as a lower limb DVT prophylaxis, also as an exercise device. Okay, so this is purely a surgical device, a targeting system, which is kind of very essential in the sense. So where do the doctors or the surgeons burr the hole when they are trying to do a neurosurgery, when they are trying to do a located tumor? So generally the practice is they get 2 to 3 days before they get the CT scan done. And once the CT scan is done, the doctors identify tentatively what is the region and then start drilling the hole or doing a burr hole. Now this could be a very, it could be statistically, it could be very little bit erroneous because they may start burring a hole in a slightly different region. And then they may realize it later, no, this is this point represents some other point in the CT scan. So can we have a targeting system at least? I mean, going forward, we'd like to have a drilling system, but essentially a targeting system which will help in identifying the correct uh, region within the brain and then start burying the hole there. And so what we wanted is a system where it captures the CT scan results and then develops a 3D point cloud system of the human body, of the human face here, and then it can then identify the particular point. So having a robotic system helps here is because the robot can actually then go and then point out to that particular specific point. Now the second challenge here is this is in one particular frame, and the patient lying in this particular bed in the surgical bed scenario will be completely in a different frame. So we need to have some kind of a frame transformation so that then this particular whatever the doctors identify the tumor location can then be transformed into the patient space, right? So for getting the patient space, I think we need to have some kind of an intraoperative space, um, intraoperative scanning result. So that is possible with the Kinect IR sensors. So I think Sriram and Pavan and Pon Deepika was the RA from the Minro. So they developed this particular overall system wherein the co-registration between the CT scan, which we call it as an pre-operative, right, happens with that of the intraoperative, the IR results. So intraoperative, that is on the surgical table, and it aligns, the registration is done. Once the registration is done, we exactly know which point, and then I think this particular the targeting system can actually move to that particular position. The other problem which normally the surgeons face is when they are burying the hole, the hand can get a little bit misaligned. So it is not, when they are burying a hole, burying a circular hole or a line or something, it needs to be perpendicular always on a surface profile here. So the head, this becomes a very, the profile is not very straightforward. So if I'm having piercing or something, it has to be at every point of time, while it is piercing, it has to be normal with respect to a point on the surface. Right, so that has been handled. The Sriram developed a mechanism wherein it identifies the surface, and then this the needle here or the targeting system is always perpendicular to that particular point in the surface. So I'll just show you a video wherein, although we don't have the complete tool flow, I think we have a tool flow from the IR scan, which is the interoperative scanning results, how it looks how the 3D point cloud system is created, and then how the robotic targeting system is actually moving. Right, so I'll just show you this particular video. So here is the table, and then I think this is a 3D printed head here. So it has been done, and then within this setup, the IR scanning is going on, where it reconstructs the 3D point cloud of the of the head. And on this, we have identified some points where the drilling head is moving, and then at every point it becomes normal to this particular points on the surface. Right? It tries to adjust and then tries to be normal at every point. So here is the side view. And then if if there is a surface or a circular path, I think that is also being done by this particular system. So once we get a series of points, then becomes easier to act and become reorient itself to become normal to every point in the surface. Okay, so I'm moving ahead. So this system was actually not intended for operating microscope, but we eventually applied it as an operating microscope. The reason is we started with an objective of a single port incisive tool, single port in the sense whenever there's a laparoscopy or a neuroscopic surgery, there are multiple points that needs to be inserted by the surgeon, so that in one side you can have a probe, the other side you have some kind of a cutting or a suturing tool. And then so there are multiple ports that are being, or the holes that are being created in the body. The intention here is to develop a single port system, single port as well as the tool navigation system within the single port. Right, so with that particular aspect in mind, what we try to develop is a single port has to be hollow enough so that it can transport all other cutting tools or the suturing tools, the suction tools and everything. Right, so I'll just run through a video and then once again come back to where we are now. So this, we say that this is the flexible probe, right? Because we want it to be a kind of a single port. It has to easily maneuver around the human body wherever we want it. So we wanted a very hyper flexibility, the nature of the probe, and it has to be hollow enough. And also it needs to have some kind of a spaces. So in the inside, it is kind of completely hollow. And then this particular slots are created so that we can actually move, we can actually bend these individual probes. Right? So if I say that if there are two such entities, it could be moved to 29 degrees in any of the directions. So if I have such 6 of the entities, ideally I should get 29 degrees multiplied by 5, I think. But I think we are getting a maximum of 70 degrees, somewhere close to 70 degrees of the bending. Right, because that is purely because of the way we are bending, we are using the pulley system. Again, each of the entities are actuated by the threading system. So this whole portion is hollow. And we have the slots here so that we can have the threads going on and then attaching it. And then if we can move, so if there are 3 threads, we can move in either of the directions. All right, so this one gives us not really 3 degrees of freedom, it gives us 2 degrees of freedom, the yaw and the pitch. And this one actually gives us the vertical motion and one more motion in this particular direction. So effectively, we are getting 4 degrees of freedom, but eventually I think it should be easy to get the 5 degrees of freedom, the Z, X, and Y, and as well as the 2 angular motions here. But because of its size, the size is around 2.5 to 3 centimeters, the outer diameter, I think you cannot directly realize this in the neuroscopic purpose. So what we did was we had attached a camera here, which is kind of a regular medical endoscopic camera at the tip of it, and then that is kind of fed through the that is the wire. It is wired and then taken externally and then put into a display. And then we also attached an accelerometer. Accelerometer helps us in regaining our orientations whenever we want it. So we have used this for a completely different purpose. As an operating microscope for doing the brain dissections. So the surgeon or the doctor from the demands came and then did all the brain dissections. And then with little movement here on the base side, he was able to move this particular flexible probe and then get the oblique field of view, which gives us more information, which gives the more information to the doctors who are doing the brain dissection. So this is basically a real brain dissection which has been done in the 315 lab. Right, and then this is how the brain, cadaver brain, looks like while it is undergoing the dissection. And this is the trajectory plot of the probe, where we can actually determine how much of the movement the probe is done, and then also we can inversely state that whether uh, the surgeon or the doctor who is actually performing the surgery, whether we can measure his, whether we can assess his skill sets. So generally, the doctors, while they get experience, they will do the minimum movement. They know exactly where to dissect and all those things. So kind of we can also employ it as a tool for measuring the or accessing the skill levels of the doctors. Right. Again, this was completely done by Arvind Ramkumar and then Ronak Doshi of 2017 batch. Arvind Reddy had started this 2015 batch. Arvind Reddy had started this in a two-dimensional manner, and then so these guys did it for the three-dimensional, so that is moving in the making it 4 degrees of freedom. And Dr. Kirit Arumula from NIMHANS actually came and then did utilize this particular the probe, flexible probe. Right, so I'm now shifting towards the edge device. So all these are the robotic devices which we have developed in the lab, and so as per the definition, the edge device means we need to have some kind of a sensing as well as the decision-making ability within that particular small aspect of the device. So generally, I think the patient management is something we generally tend to not address, but it will be nice if the hospitals can themselves take upon themselves and then do the patient nutrition management. So once the patient is kind of discharged and he goes back to the home, what kind of diet or what kind of nutrition the patient can have. So I think we have a strong collaboration going on over the past 2 or 3 years with Professor Sazonova from my alumni, University of Alabama, and his team. So they were working on this particular device. Although this device was developed with lot of suggestions from our students also. Vinay Krishna had gone to do the internship there, and then they have developed this small camera device which sits. No, this whole thing actually sits onto the spectacle, and it captures the food intake of the person, right? So Ajay now has started, and then Prashant. So Prashant is working purely on the wireless communication. So this particular device captures the food and then connects it via the Bluetooth to the smartphone, and then from the smartphone it actually goes to the cloud, and then from the cloud it actually does all this, the detection. So Ajay primarily worked on this to get the bounding boxes. So now these two images are very staged images, so not really a real time. Whereas this one, I think he has the very recent results, last week results, where I think he has applied some different, altogether a different method of graph cutting methods and all, and then identified the types of food within or the different colors, the different types of food in a plate. So generally, he started with this particular technique of YOLO V5 and then some data augmentation techniques. But still, it is still the decision is done in the cloud. So that's why I call it as more of a wearable and an IoT device. But if we want to make it as an edge device, it will be nice to have it the decision-making ability on this particular small device. So what we are trying to do is put it onto an FPGA design, and if the FPGA design, if it can actually detect the bounding boxes, then I think we can do the go ahead and do the RTL design and then realize it as an SoC chip. So parallelly, I think Sanjay was working, my MS student. He has been working on the FPGA and then the edge computation. So he's been developing to develop that particular object detection. And so he has, to some extent, I think he has realized the object detection using this particular mobile net version 2, which is kind of a very lightweight. And he's trying to realize it on a specific FPGA board. This one ZCU102 has a very large resources, large VRAM. And we are hoping that by the end of his thesis, the foot detection application could be identified. And of course, he has tried some techniques of optimizing the hardware. Just in the deep neural networks, I think the first few layers of the CNN, I think he is trying to use the depth-wise convolution so as to reduce the parameters and in turn reduce the hardware resources, which is which could help in the edge computing. And he has also tried, instead of the full precision, I think he is trying to use a half precision floating point format, thereby reducing the parameters and then the activations. Right. So this is still an ongoing work, but I felt this is kind of very important in the context of the nutrition management, wherein we should be able to do the object detection on the device itself, on the FPGA. And FPGA is a kind of a very useful resources because it works as a co-processor, and then the whole of the neural network can be hardware programmed in this particular FPGA device. This is kind of very unique, and then I felt it is kind of very new project. Not much work we have done. It's kind of an automated dosage injector based on the EEG signals. So what we really need is for the epileptical patients, they generally get this seizure attack, and once the seizure is it's been attacked, it becomes really difficult to identify which parts of the temporal lobe the seizure has started. The onset of the seizure becomes really difficult to identify. So generally, there is an ICTAL SPECT, which is kind of an instrument, or you can call it as a scan results, which is done on the epileptical patients. And whenever there is a seizure attack, the onset of they try to measure using this ICTAL SPECT scan results. But the problem is it's very random in process. The seizure attack is kind of very, very random in process. So currently, I think the hospital does, there is a nurse sitting beside and then continuously monitoring the patient. And if, whenever there is a seizure attack, the poor nurse has to be awake all the time, and it can occur at any point of time. And then she or he has to give an injection. Now, the overall process has a lot of manual intervention. So can we make it a completely automated dosage? So for making it a completely automated dosage, what we need is, the seizure prediction. Now, the seizure prediction can be done using the EEG set of signals. And then once the EEG signal is kind of detected, if it is predicted, really not a detection, if it is predicted at least half an hour early, right, then this prediction unit can turn on the injection dosage, and then the injection dosage can then be given to the patient. Right now, this particular injecting dosage is basically a radioactive material. It's a radioactive dosage, so that it works like a tracer material, and then goes through the veins here, and then goes to the brains, to the region of the brain. And when the seizure occurs, it can actually highlight it. It can really highlight in the ICTAL SPECT. So to just introduce the dosage system here, the radioactive dosage system here, so we need a very good predictions unit. So earlier, I think Krishna had developed a lightweight classifier, and then he had developed this kind of an injection system wherein, based on the EEG signal predicting the seizure, there is a dispensing of this particular liquid. But although I think the lightweight system was not so accurate, so I think now I think Ronak and Arvind are working on it, and hopefully we will have the prediction algorithm working soon. The second one is, we are also trying to plan moving towards an optimal hardware accelerator edge device in the FPGA again, and realize it again as an SOC solution. Right, so very similar to the foot detection problem, I think. So Saujanya is working on this. So what we really want is an EEG-based seizure prediction problem, or rather the deep neural network. And then if that network can actually be deployed into the FPGA, which is I've written here is as a Zinc device. Some part of it, so the whole network will actually go into the programmable logic, and then the processor, which is there as a single chip solution, can handle the other portion. So the overall network and then the weight parameters and everything will go into this programmable logic, which will make it faster. So the seizure prediction becomes kind of a very real-time event, and the faster it is, the better it is. So the better, in the sense, the radioactive dosage tracer can go into the body quite early, and then it can highlight the onset of the seizure very nicely. So the prediction problem is nothing but the interictal and the preictal states that could be observed in the EEG. Now this, it's a challenge, but I think if we get a particular neural network, I think it can easily go into here. So I think Saujanya, Ronak, and Arvind are working on that. This problem was actually given by Dr. Chandana from NIMANS through Dr. Vikas, and I felt it was kind of it has both aspects of prediction as well as the robotic injection system. So I'm slightly deviating now away from the medical care system, and I felt that this needs to be introduced because students have worked on this for almost 1.5 years. So it's a kind of a passenger anomaly detection. So even without intruding to the passenger within the cab, passenger sitting in the cab, can we identify whether the passenger is in a harassed state or an abused state or mentally, he's in a different state. So without using the camera. Now, so what we developed was, an array of pressure sensors putting onto the back seat, on the back rest, as well as onto the seat, and having this is kind of a sensors which goes here inside the cushion, and then wire it up with currently it is an Arduino Mega or something, and so we have this particular cushion sensory system ready, and this is kind of tested onto the real car in-cabin sensory system. So actually the idea started with Pranav worked on this, and Pratyush and Anubhav has been working on this for almost more than 9 to 10 months now. So they were able to develop this and then test it out, and then so we did not use the machine learning initially. We tried to using a signal thresholding method, and then it gave some good results. Now I think now that the data is anyways captured, they've tried some SVM methods on the offline data, which is showing the good results, and then they want to put it into a Raspberry Pi or a Jetson board, make it as real time as possible. And moving forward, can we realize it as an SOC solution, validate it with on an FPGA, and make it as real time as possible. So Ajay, who is a sponsored, Ajay is a part-time MS student. So he worked on a similar application, but looking at the camera. So once you have the camera, can we run the facial emotion recognition algorithm and on the FPGA? But the FPGA is kind of used only for as an acceleration purpose. So it is the whole of this neural network is actually not there in the FPGA. So only the MAC unit, the multiply and accumulate unit, is actually put into the FPGA, and all other is done in the processor part. And it turns out that the FER for his own images is kind of working well. So it recognizes, I think, 6 states. So ultimately what we want is to validate the facial images, the facial emission emotion recognition system with that of the sensory system, in-cabin sensory system, and then say that, okay, it gets validated. So the person is really in a particular state, what he is in. So then it could be actually be deployed onto to the real-time scenario. Right, I think this is possibly the last set of slides I have, completely away from the medical care. So this is the approximate computing for the image processing algorithm. So generally the approximating computing is an ongoing work which helps us to realize the applications. And there are 2 advantages. One is it doesn't affect the application as such. And the second point is it reduces the power, the delay, and then the area within the chip. Right. The other advantage of the approximate computing, the overall thing is this can actually sit as one of the operations in the deep neural networks, and then we can retrain the model with the approximated computing modules. And then, so because of the approximate computing, the resources that will be used in the FPGA system or in an SOC realization will be very, very minimal. So in that sense, we had started this work, and approximate computing here, I think we have shown a 32-bit approximate full ladder design with some kind of a approximation, 5 to 6-bit approximation. And here the approximation is on the lower side, LSB side, and then the higher MSB side is not touched. So it is a exact adder, and the inexact adder is there only on the LSB side. So here is one thing where the last 2 bits are we had to consider it as 1, and the other 2 bits, I think it doesn't uses XOR at all. It just uses the OR for getting the sum. So it is fairly an incorrect results, but because being employed in the LSB, the incorrectness or the error we get will be very, very less. And then when we actually realize it using the ASIC flow, I think it gives us a very good, ED, whatever, the power, delay, and area, the product of it will be very, very less. And if I put it onto the application level, realize this in a MATLAB, this particular logic, the bitwise logic, and then put it into an edge detection algorithm. So this is the original image, which after the edge detection, it gives me the exact adder. If at all the exact adder was there, this is what the results are. But with an approximate adder, the results are not bad. The PSN, the SNR value of this output images is quite acceptable. So there's a lot of research going on that, the approximate computing. And so here is possibly my last slide, where I think Shalini is working on the reverse carry propagate full adder along with Sai Teja. So what it really does is generally the adder are considered to be a carry ripple propagate, forward propagate adder system. If I have a reverse one, the advantage is even if I even if I violate the timing constraints, right? Even if I violate the timing constraints, so because the propagation is in a reverse direction, the LSB bits, the results of the LSB bits, which doesn't have that much of weight, right, will be affected. Right, in a normal adder, in a normal carry ripple propagate adder, so starting from the LSB, it goes to the MSB side, and if there is a violation, the MSB weights are very, very higher, and then that will have a major effect. And that's why I think she is trying to realize the carry, counter flow of the carry counter flow of the carry propagation. And I think at the same time she has tried to realize the DCT based compression algorithm, and which fairly gives a good results. I think somewhere around 87% of the structural similarity index matches with that of the exact adder, right? And I think this one particular image is, and I had to state this, Bhargav and Sairam, they have got a novel approximate divider. So generally the approximate divider they have done, and generally it is seen using the Taylor series, but I think Bhargav and Sairam had worked on the approximate adder using the Newton-Raphson method. And with some decent progress, I think they have got these 2 results, the original one and then the color quantization application, right? With giving a sufficient and an adequate structural similarity index. Right, so we have this approximate computing, which can then be backpropagated into the, the realizing the deep neural networks into one of the, in several of the layers, and then we can retrain that, and then that can be used for any of the video or the image applications, which fits in well to the either the seizure prediction, looking at the facial tracking of the patients. We can actually use it for the seizure predictions also. So in that sense, I think the approximate computing is kind of useful, but at this point of time, it is slightly away from what the medical care applications we have been trying. Right, so I think that's it from my side. I'll just try to acknowledge all the funding agencies. Thanks to the University of Alabama, the IBM Shared University Research Grant helped us to develop the Surface-EMG system, and so the Young Faculty Research Fellowship has helped into explore different areas. This one, the MSJE has helped us to develop the Anthropomimetic upper limb device. And thanks to MINRO and EHRC support, I think we have got some good research associates, and then the students working on it continuously. And think I have one more slide. So thanks to again Dr. Vikas and all the faculty from NIMANS. I think there have been a lot of ideas, and at our own pace, we have been able to do it. So there's never a pressure on delivering or giving the results. So that is one important point which we like about this collaboration. IIIT students, I think IMTech 2015 to 2017 students' work have shown here. There are a lot of students who have been working, including I think the 2018 students have started working now. The MTech students, I should not forget Dheeraj and Prajwal and all those who started with the ventricular assistive device, and were a part of it, Prashanti as well. And there are other MTech students who have worked, possibly not in this particular area, but at some point of time they have been able to support or give us some ideas on this particular solutions. Samsung MTech, I think Sharmila has been very encouraging for us, and she has now joined us as a PhD student, so that gives a lot of satisfaction. And the MS students, starting from Sanjaya, Saujanya, and Shalini, and of course all the IIIT faculty and staff, they have been there always whenever I wanted. Thanks to Professor Shrikant, Professor Das, Professor Subhajit, and Professor Chetan, Professor Murlidhara, and everyone else. Yeah. Staff Adisai and Ashwini, I think they have been really nice. So with my constant demands, yeah, I think that's about it from my side. So thank you everyone for joining.
Thank you, Madhav. That was a great talk. Thank you so much. There are several questions now, so shall we take one by one?
Yes.
Okay, I'll first start with the questions in the YouTube chat, so that there are two questions there. We can finish that first. So the first question is, Madhav sir, instead of gripper finger will be more efficient, and Arduino is 8-bit machine, less response than 32-bit machine. 10 slide. Can you explain, please?
Yeah, I think that's a very good observation. Whoever has observed it, this is an Arduino based system. And if you actually closely look into it, I think I've shown the recorded video where the motion capture was actually not a real time. So we captured the motion and then we try to replay that. So in the sense, because we are using the Arduino system, I think that's why it is not effective. Ideally, I think an STM32 microcontroller or an Raspberry Pi should be more than beneficial here.
Okay, there are questions in the chat here, so I'll start. Anirudh KB has asked, what is the target mass, like how many grams that the end effector must hold? This is with respect to slides 10 or 11. Vishal Katani's 8 degree of freedom.
Yeah. I think Anirudh, I have not characterized it, but I think these motors are pretty good. Robotics motors, especially I think the AX and MX series. So the shoulder is pretty good. If I look into the data sheet of this MX series, I think it says 110 kgs or something. But on the gripper side, I'm still not sure. Maybe around still oscillating. So I think maybe around 4 to 5 kg it could comfortably hold, but without oscillation, that needs to be characterized.
How do actuator technologies compare? Example, semiconductor processing uses air bearings, but it is too much for this application. Other than safety, have you used magnetic bearings in the joints? Regarding this FPGA, can it provide the actuator drive also, or you need a separate power amp?
No, magnetic bearings in the joints could be, I think that could be a very useful idea. But no, I think we have not utilized. So most of our work we have done only the electromechanical actuation. So not any electromagnetic based actuations. The reason is it somehow introduces more complexity, I think. And then I cannot realize, and that's why I don't allow students to do the magnetic based solutions. That's the answer. Yeah, FPGA, can it provide the actuator drive also, or you need a separate power amp? Yeah, the separate power amp could be useful. The FPGAs can only work as a switching logic.
So Ram has asked, what are the regulatory processes and requirements in adoption of such technologies in actual surgeries?
Yeah, I think.
And Prasanna has continued on that, asking, does ICMR have standards for these to be deployed?
So, Professor Ram, regulatory process. There is a regulatory process set up by the CMR. Uh, I forgot the name. It's generally there for all the electronics products, and that has been now been introduced for the medical or the surgical field also. And yeah, the one thing I think I realized that in this particular field is I mean, there needs to be a lot of finance for getting even the regulatory things done, getting the product done first, and then uh, use that product for getting the approval for the regulatory process. And that is, I think, beyond our imagination. Maybe so. That's why we're not really thinking about this process.
Thank you so much, Madhav. I think it's been wonderful, and it's a lot of projects, and most of them are quite successful as well, right? So it's been great run for you, like in the SARL lab, right?
Yeah.
And congratulations for all your publications, and
Thank you. Yeah.
the students are doing great. So this is great innings. Good
Yeah.
job.
Yeah. Thank you. Thank you, Jen.